Welcome to my presentation. My name is Vania Arulmathi. My matrix number is 224385, and I am presenting for my subject Thermodynamics 1, code EMM3226 1, taught by my lecturer, Dr. Noureddin, and my presentation is entitled Fundamental Principles of Thermodynamics and Internal Combustion Engines. For this subject, we were given an individual assignment where we were supposed to write on the first and the second law of thermodynamics, which are the fundamental principles, and we were required to connect it to a complex engineering system. And in my case, I have selected internal combustion engines. First, allow me to give a little bit of introduction to thermodynamics. By definition, thermodynamics is the study of energy, its transformation, and its interaction with matter. Why thermodynamics is relevant to us as engineers is because it is foundational to engineering systems like engines and power plants. And it also impacts daily life from household appliances to industrial processes. How it affects the industry is in terms of the construction or the generation of energy in terms of steam power plants, hydropower plants, fuel production, petroleum production, so on and so forth in the chemical engineering industry, and how it is relevant in household appliances are in terms of the refrigerator that we use or air conditioning system or basically anything that converts energy from one form to another. Now, as mentioned, energy can take two forms, two main forms, which is heat and work. Now, as you can see in the diagram on the right, it classifies energy contained in system by specifying whether it is positive or negative. So, work, let's take work. First of all, work done on the system will be positive, but work done by the system will be negative. And this is the opposite for heat, where it states that heat that is absorbed by the system is positive, but heat that is released by the system is negative. Now let's look at the first law of thermodynamics, which is the very core principle in this subject. The first law basically talks about the conservation of energy. It states that energy can neither be created nor destroyed, but it can change from one form to another. The basic principle of the first law is delta E equals to delta U plus delta KE plus delta PE. E refers to energy, U refers to internal energy, KE refers to kinetic energy, and PE equals to potential energy. Delta refers to the change that's happening in the system. Now, usually kinetic energy is seen in a system that has any moving parts, and PE or potential energy is seen in a system that has elevation. And internal energy is for systems that are considered as closed systems. Another equation that is correlated to the first law of thermodynamics is that delta E of the system equals to the sum of the difference in heat and the difference in work, also known as Q in minus Q out plus W in minus W out. Now, an example of the application of the first law of thermodynamics is the drinking bird. The drinking bird, as seen in this picture here, relies on the energy that it gets from the cup of water to power its movement. Now, how this works is that the bird is usually filled with a fluid that has a lower boiling point. So it can easily change from a gas to a liquid back and forth with just a slight change in temperature. The slight change in temperature comes from the water that it is dipping its head into. Now, the drinking bird, as you can see in the picture, has some red liquid at the bottom and some vapor at the top of its head. So, what happens is when the bird's head dips into the glass of water, it gets wet. So, it keeps bobbing back and forth for a while, and as the water evaporates from the head of the bird, it cools the vapor in the bird's head, which condenses into liquid, creating a partial vacuum in the head of the bird. Now, that is what makes the liquid travel up to the tube. Now, as the liquid slowly travels upwards, the head gets heavier and heavier by the second, and it dips back into the water. But the tipping makes a bubble rise through the liquid into the bird's head, sending more liquid back down to the bottom and setting the little bird swinging back and forth, and thus this cycle continues as long as there's water in the glass. Now, but it still needs water for it to do its thing. Once the water in the glass runs out, then it won't be tipping back and forth anymore. Now, there are four basic types of processes where the thermodynamic properties of a system, generally an ideal gas in some kind of container, can change according to the first law of thermodynamics. In each case, one property is held constant, either volume, pressure, temperature, or heat, while the other properties change. Variation on all these properties are used in all kinds of machines, especially heat engines or engines. First, there is an isovolumetric process where the volume is held constant, usually because the gas is in a rigid container where while heat is being added or removed. A rigid container means the volume remains constant because it is not moving, there's no space for it to move. Now, as you add heat, the pressure of the gas in the container will increase, and so will its temperature. As you remove heat, the pressure and the temperature will decrease. So, the isovolumetric processes are very simple, and as you can see in the PV diagram here, the volume decreases, the volume remains constant as the pressure decreases. And the work in an isovolumetric process will always equal to zero since the volume is unchanging. Now, the second type of process in a closed system is known as an isobaric process, where the pressure is being held constant while heat is being added or removed. And it is slightly a little bit different from the isovolumetric process, as you can see in the PV diagram. Here, the volume of the container is allowed to change, usually because the gas can move due to a piston, either frictionless piston cylinder or a normal piston cylinder. So, as you add heat to the system, the volume and the temperature of the system will increase, and as you remove heat, the volume and the temperature will decrease. This means that an isobaric process can do work, and the formula for work is given by P multiplied with the difference in volume. As you can see in the PV diagram, pressure is held constant while the volume is increasing from one point to another. Now, another type of closed system energy process is known as the isothermal process. In this process, the temperature is being held constant. So, usually, when the temperature is being held constant, it is usually done so by connecting a system to a much bigger system whose temperature would take a lot of heat to change, known as the heat reservoir. The heat or volume of the system is then changed very slowly so that the other properties can adjust while the temperature essentially stays constant. An isothermal process is kind of similar to an isobaric process in the scenario where if you add heat, the volume will expand, so the system will do work. But for isothermal processes, you can't use the same formula as the isobaric process where W equals to P multiplied with the change in volume. Instead, we need to take the integral of the pressure with the respect to volume. This way, we can still calculate work, but we're also taking the changes in pressure into account. Another difference between the isobaric and the isothermal processes is that since temperature is being held constant in isothermal processes, the internal energy of the ideal gas cannot change. And the first law of thermodynamics says that heat minus work is equal to the change in the internal energy of the system. In this case, zero. So the work done by the system will be equal to the amount of heat added, also known as Q, and vice versa. So that is why you can see in the below the graph it says that the formula for work equals to Q. Now the final type of processes in the first law under the first law of thermodynamics is an adiabatic process, where no heat is allowed to flow into or out of the system, but the fluid within the system can expand or be compressed. Again, the equation for the first law of thermodynamics is helpful in forming the equation for work. Q is zero in an adiabatic process since heat is not being transferred into or out of the system. However, the internal energy of the gas can change. So this means that the system can do work or have done work have work done onto it. In fact, the change in the internal energy of the gas will be exactly equal to the negative of the work, which is why, as you can see below the diagram, we can see that the symbol in front of W is negative. And thus the formula for work is given as negative W equals to the change in the internal energy. Now let's take a look at the second law of thermodynamics. The second law of thermodynamics states that the energy transformations are directional, meaning they occur in a way that increases the overall entropy of a system and its surrounding. Entropy, usually symbolized by the alphabet S, is a measure of disorder or randomness in a system, representing energy that is no longer available to perform useful work. The core concept here is that the entropy of a given system or even our entire universe at any given moment is constantly increasing, meaning that the state of matter in our world is constantly increasing in terms of chaos. There are four key concepts in the second law of thermodynamics. The first is the Kelvin Planck statement, which states that it is impossible for a heat engine to operate in a cycle and convert all heat into work without rejecting some to a low temperature reservoir. This sets a theoretical limit on the efficiency of heat engines and emphasizes the inevitability of energy losses. This means that for a given cyclic system, for example, a power plant, energy can never equal to 100% because there is heat that is flowing into the system, but there will also be heat that is being wasted. We cannot avoid the heat that is being wasted. The second concept is the Clausius statement, which states that heat cannot spontaneously transfer from a cooler body to a hotter body without external work. This principle explains the need for energy input in devices like refrigerators and heat pumps, introducing the concept of irreversibility in thermodynamic processes. So, previously, the Kelvin Planck statement mostly focuses on heat engines, which are known to be reversible. However, the Clausius statement focuses on systems like refrigeration circles, which are known to be able to be irreversed, meaning it flows in the other direction as well. So, the third concept is reversible and irreversible processes. So, reversible processes are idealized and occur infinitely slowly without dissipative effects, allowing the system to return to its initial state. In the real world processes, reversible processes are due to factors like friction, unrestrained expansion, and heat transfer through finite temperature differences, leading to inefficiencies. The fourth concept, and what is perhaps known as the key concept in the second law of thermodynamics, is the Carnot cycle. So, the Carnot cycle is a theoretical model of the most efficient heat engine operating between two thermal reservoirs. So, the thermal reservoirs, we have the energy source and the energy sink. So basically, the Carnot cycle comprises of two isothermal and two adiabatic processes, setting the maximum possible efficiency based on the temperature difference of the reservoirs. So as you can see on the graph in the image attached, there are four main points. So from the first to the second point, the process is known as a reversible isothermal expansion. Between the second and the third point, it is known as a reversible adiabatic expansion. Now, from the third to the fourth point is known as the reversible isothermal compression, and from the fourth to the first point, uh, back to the first point, is known as the reversible adiabatic compression. So we can see some similarities here between point 1 and 2 and points 3 and 4. It is known as an isothermal process because temperature is being held constant, whereas between points 2 and 3 and 4 and 1, it is known as adiabatic because there is no heat flowing into or out of the system. And all of these individual systems are reversible, meaning it can go clockwise or it can go the other way around to achieve maximum possible efficiency. So, in this assignment, The first part where required me to analyze the first and the second law of thermodynamics as I have done, and the second part of the assignment required me to apply these concepts to explain how a specific complex engineering system works. And the engineering system that I've selected is an internal combustion engine, also known as ICE, which are found in most motor cars. So, allow me to give an overview on the internal combustion engine. So, the key components involved in ICE are the combustion chamber, piston, crankshaft, and valves. The energy flow within the ICE can be described as changing from chemical energy to thermal energy to mechanical work. Now, there are some challenges that is faced by an ICE, which includes balancing efficiency, emissions that are produced due to the fuel that is used by an ICE, and the overall cost of an ICE. So, how does the ICE correlate to the first and second law of thermodynamics? Let's take a look. In the first law mainly focuses on energy balance, and how the ICE falls into place here is that the heat input from fuel combustion, the work output via mechanical motion, and the heat losses to the environment makes up the overall energy balance, which is the key concept of the first law of thermodynamics. And some of the engineering goals which correlate to the first law of an ICE is to minimize frictional and heat losses and to enhance fuel to work conversion. In doing so, it is able to achieve not 100% but maximum possible efficiency. So, how an ICE correlates to the second law of thermodynamics is in terms of the impact of entropy. So, as we know, the irreversible processes tend to reduce efficiency, and how ICE is known as an irreversible process that can reduce efficiency is because it has exhaust gases that represent energy and entropy loss to the system. Now, there are some solutions for this engineering problem. The first is turbocharging to recover exhaust energy, and the second solution is advanced combustion cycles, such as the Atkinson or Miller cycles. Although most motor cars uses an ICE, there are several conflicting priorities that take place in terms of concerns for the environment, concerns for energy, concerns of engineers, and back and forth. So the first concern is efficiency versus sustainability. That is because higher efficiency of an ICE can lead to higher nitrogen oxide or NOx emissions, because in order to achieve higher efficiency, it has to use a certain specific type of fuel with a certain ratio, but these specific types of fuel tend to have higher harmful emissions. The second conflicting priority or the concern here is performance versus cost. So, usually for an ICE, advanced materials and technologies are required to achieve a better performance of the ICE, but advanced materials and technologies tend to cost more. And so the third conflict that is faced by an ICE design is entropy and environmental impact. As I mentioned earlier, entropy is basically energy that is constantly increasing in the system. So energy can be in the form of heat and work, and for an ICE, it tends to have a lot of waste heat that it is producing, and waste heat recovery tends to reduce entropy, but it is known to add complexity to the system. Now, to recap everything or to summarize everything that I've presented here, I have talked about the first law of thermodynamics, which governs the energy conservation and transformation. I've also talked about the second law, which addresses entropy, directionality, and efficiency limits. I've also talked about the applications in an internal combustion engine, which is to optimize energy use and to manage inefficiencies and environmental impact. And I've also discussed future directions in terms of sustainable and efficient engine designs that can leverage both the thermodynamic principles in order to achieve maximum efficiency, reduced effects on the environment, and overall increased performance. So, to conclude everything, Thermodynamics provides essential insights into energy systems. Internal combustion engines exemplify the practical application of the first and second law of thermodynamics, and continued innovation is necessary to address efficiency, cost, and environmental concerns. Now, before I end my presentation, I would like to express my sincerest gratitude to my lecturer, Dr. Nordin, for being so supportive and understanding during my presentation preparation, given the circumstance that I had to deal with. Your guidance throughout the semester has been invaluable, and I am truly grateful for the opportunity to share my work with you. Thank you once again.